you need extra help with this, or if you are gone. So, all right. So what do we got here? So number one, we learned that the average velocity is found by taking what? By taking blank divided by time.
Displacement.
Displacement. Okay. So we take the displacement. Displacement divided by the time. Remember, displacement is delta D. So a little vector over that. Divided by time, or the equation would be that change in position over time. That's an equation. On a curve, the average velocity is the slope of the line connecting 2 points on the curve. Okay? So if we have a curve and we have 2 points on that curve, what's that line called we use to connect 2 points? Okay, so let's say we have a curve like that. Okay, we have 2 points, one right here, one right here. We connect those 2 points. What's that line called? Anybody remember?
Secant.
Yeah, secant. Good. That's the secant line. Okay, that's the secant line. What I'll do is I'll hand out rulers to you guys, because you're going to need rulers for this. So let me hand. Okay, so oops. Scrolling down here, let me get a line. That'll be the secant. Okay? And the secant, guys, the secant line will, the slope of this actually gives you the average speed, or the average velocity. It averages the velocity out. As you know, so you look at the slopes along the curve of this line. It starts out with a slope of almost 0, right? And the slope increases, and then decreases again. If we took all those values and averaged them out, you'd get the slope of the secant line. Okay? So the secant line actually represents the average velocity. It represents the average velocity here. Oops. Okay? Any questions on that? Oops. Let me get these words back up here. Okay. Next, to find the velocity at exactly 1 point. What do you think that's called? The velocity at one specific moment in time. At any instant. It'd be called the instantaneous velocity. So to find the velocity at any specific point. So guys, using displacement over time gives you an average velocity. It takes the velocities that are changing and averages them out. We can actually figure out what's called the instantaneous velocity. We can do what's called the instantaneous velocity. Okay, this is found by taking the slope of a tangent line. Raise your hand if you know what a tangent line is. People in calculus, right now, you should definitely know what a tangent line is. Okay? So this is the key idea here with this, is that the instantaneous velocity is the slope of the tangent line at any instant. A tangent line is a straight line that touches the curve at only 1 point. Write that down if you don't know that. Okay? It touches the curve at 1 point. So if I have a curve that looks like this, and I want to draw a tangent line for right there, okay, the tangent line, let's pretend that's on the top, would look like this. Okay? It's a straight line that touches the curve at only one specific point. Does that make sense? Okay, if you look at because if you look at a curve, it can only touch at 1 point. Okay. So let's get rid of this line here. So, draw the tangent lines, it says, draw the tangent lines at 1 second, 3 seconds, and 5 seconds. So you can do that right now with your ruler. Draw the tangent lines at 1 second, at 3 seconds, and at 5. I just drew the tangent line exactly at 1 second, and if you look very closely here, it's touching the curve at exactly 1 second. And that's the only spot in which it's touching the curve. You see how that works? Because if you zoomed in on this and you found the slope at exactly 1 second, the slope of that curve would be the slope of that tangent line. Okay? Looking at get the tangent line at, what is it, 3 seconds is the next one? At 3 seconds here, we change the color like blue. Okay? Would the slope increase or decrease from at 1? It would increase, right? The slope would be steeper. So at 3, there's the line right here. I know it's going to be touching the curve at more than 1 point, but you want it to represent the slope at that specific point. Okay, so I'm going to try and get this right at 3. That's where it's the steepest, looks like. Well, right there, right? Is that good? So yours looks like? Okay, so that's the tangent line. It's touching right there, right at 3 seconds, right at that point. Maybe go up a little bit more. And the last one would be at 5 seconds here. So let's look at 5 seconds. Looks like the slope gradually is approaching 0. So at exactly 5 seconds, it's almost exactly 0 at the end. It's about right there, right? Maybe go right there. Okay. So again, what I did is I looked at the points. Okay, right here at 3, and right here at 5. And these tangent lines are only touching the curve at one specific point. You have to understand tangent lines before we move on. Okay? You have to understand the concept of tangent lines. Again, it's a line that touches the curve at only 1 point. Are there any questions on that? Does that make sense? You guys did that in calculus, right? You played around with that for a while? So let's look at this. The slopes of the tangent line increase from, okay, so at what times is the slope increasing? From what time to what time? Well, what's the slope at 0 seconds? Right, it's flat, right? Which is a slope of 0. And the slope's gradually increasing. So what you do is you take the ruler and you can take the ruler and have the ruler be the tangent lines and see how it moves throughout the path. So it's increasing until it reaches a maximum slope at 3 seconds. So the slopes of the tangent line increase from 0 to 3 seconds. Increases from 0 to 3 seconds. If you take your ruler, if you look at here, let me grab this meter stick. Okay, and you follow the tangent lines start like this right away, right? And they gradually increase until 3 seconds. Then at 3 seconds, the tangent lines decrease. Okay? So then, and then 5 seconds on the position graph below. Oh, I'm sorry. And then decrease from 3 seconds to 5 seconds. You can see this with your 3 tangent lines you created, right? A small slope, medium slope, and then small slope again. Okay. The increase and decrease in slope are linear. Okay, now this is another key idea. Okay, on a curve, if you follow like a parabola or some geometric curve, the slope change is linear. The slope changes in a linear fashion. Okay, so let's say I went through here and I calculated by taking change in y over change in x, the slope every 100th of a second. Okay, so I measured it 100 times from 0 to 1, and another 100 times from 0 to 2. And I did this all the way through. Okay, the difference in the slope would be linear. If I graphed it out, it would create a line. It's gradually changing. It's changing at a constant rate. Okay, so the increase and decrease in slope are linear as long as the position graph is parabolic. And that's what this is, it's a parabolic curve. A piece of parabolas joined together. Okay, does that make sense? So that's the other idea here. 3, we learned that the average acceleration is the rate of the velocity change, right? You guys know that? It's the rate of velocity change. That's what acceleration. Some of you are still struggling with the concept of acceleration. Everything to do with your velocity has nothing to do with basically your direction. It has nothing to really do with your direction. Okay? It's the rate of change of your velocity. Okay? In equation form, it'd be your change in velocity over time. Final velocity minus initial velocity over time. It's the rate at which your velocity is changing. Am I allowed to do that? Okay, any questions so far? Are we good? So on a velocity graph, this rate is just the slope of the linear section. The acceleration is called uniform if it is constant. Meaning that the velocity changes at a constant rate. That's what we were saying before. Okay, the rate at which this slope is changing is constant. Okay. A non-zero uniform or constant acceleration does not mean that the velocity is constant. Okay. The velocity is changing at a constant rate, so the velocity is not staying constant. Think of it, you're speeding up at a constant rate. That's what's happening. Okay? You're speeding up. When you have an acceleration, a constant acceleration, you are speeding up or down at a constant rate. So to summarize all of this, the slope of one graph gives the shape of the other. The shape, or you can think of it, it gives you the actual values of the next graph. Next graph. Okay, so when we do this, guys, you go from position, we use the slope of the tangent lines to get velocity. From velocity, we use the slope of those tangent lines to get acceleration. That's what we're talking about. The slopes of the tangent lines will give you the shape. Okay, so let's talk about this now. Let's find the velocity graph. Velocity, we have to look at the actual slopes of all the tangent lines to get the velocity shape. Let's look at this. What is the slope of the tangent line at 0? What's the slope right here? 0. So that means since this slope is 0, the actual value of velocity is 0. So with these, you're going to get an outline and then you can connect the dots. Where else is the slope 0? Where else is the this tangent line becoming horizontal? Where?
At 5 seconds.
Yeah, at 5 seconds. So because this tangent line right here, okay, it's almost 0. It's approaching 0. It's 0 right here. Guys, this you have to think in a different way. You have to think in terms of rates of change. Think of it in terms of, basically we're plotting the values of the slopes is what we're doing. We're actually plotting the value of the slopes. In calculus, it's called the derivative. At 3, is that a very large slope or a very small, like a very large negative slope? Very large positive or very large negative? How do you know if it's a positive slope? Because it's a positive slope if it increases from left to right. It's positive. If it decreases from left to right, that's a negative slope, right? So at 3 seconds, is that a large positive or a large negative?
Positive.
Large positive. It's the largest slope in the entire curve, right? So at 3 seconds, the slope is very large, which means the value is large. We're plotting the values. So we're plotting the slopes as values. So we'll just connect the dots, because we said since this is a parabola, the slope changes at a constant rate, which means the velocity graph will be linear. So we'll connect these with straight lines, these points, and your velocity graph will look like this. Your velocity is 0 initially. You start to speed up. Okay, at 3 seconds, your speed's maximum, and then you let off the gas pedal, and then you start to slow down until you're stopped again. Okay.